Find the natural frequency of given system.
Let us understand given system. One end of the rigid rod is connected to the torsional spring with stiffness Kt, while the other end is connected to two linear springs with stiffness K. And we have to find out the frequency for the vertical oscillation of the rod. So we will first draw the free body diagram. Now we will consider here the other end which is connected to the linear springs is having displacement x in the downward direction. So we have to show this displacement x. So this is the original position, I will say point A, and this is the final position, that is A dash. So this vertical distance is x. So x, this is the distance x, that is the motion is taking place, linear motion x is taking place in the downward direction. Now the first end is connected to the torsional spring and it is having center O. So while this linear motion is taking place in the downward direction, then about this point O, angular displacement theta is taking place. So when we join this O and this A dash, then we will get the angle theta. Now if we observe this triangle OAA dash, then this length of the rigid rod is L. So from this triangle we can say that x is equal to L sin theta. But this theta is very small, so we can simply write x is equal to L theta. So this is the relation in between linear displacement and angular displacement. Now in the direction of this angular displacement, angular acceleration is taking place. So how we can write this angular acceleration? So this acceleration couple is there. So we can also say that is the accelerating torque. So what is the formula to write this accelerating torque? So it is in the same direction of this angular displacement. So it is taking place in this direction, and that is accelerating couple or accelerating torque is I theta double dot. So this I is mass moment of inertia of this rod and theta double dot is the angular acceleration. Now for this spring stiffness K, there is the spring force. Now this spring force will act in the opposite direction of the linear displacement. So X will act in the downward direction and therefore this spring force will act in the upward direction. So if I consider this is the first spring, then I will say that Fs1 will upward direction, Fs2 is having the upward direction. So both the springs will act in the upward direction. Now how we can decide this restoring couple? So restoring couple, due to these two springs, we have to write Fs1, that is stiffness K multiplied by linear displacement x, that is Kx multiplied by the perpendicular distance from the pivoted point. So this point O is the pivoted point, so we have to multiply with L. So restoring couple we will write here as a K into X into L. Now if we observe for the second spring also the same restoring couple K into X into L. So total restoring couple due to these two linear springs we will say 2 times of K into X into L. So this is important. Now we will move for the torsional spring. So torsional spring is having stiffness Kt. So due to this stiffness Kt there is the couple. So restoring couple due to torsional spring, how we can write here? So it is equal to Kt into this theta and it is in the opposite direction of this displacement. So displacement is taking place in this clockwise direction. So we have to show this anti-clockwise direction due to the torsional spring. Here is the couple Kt into theta. Now what is the direction for this Fs1 and Fs2? So if I move the compass about this point O in the upward direction, then Fs1 and Fs2, that is the couple due to this spring force, is also in the anti-clockwise direction. Now we will consider for this clockwise direction sign is positive. Then for anti-clockwise direction we have to consider negative sign. Now we will apply the Newton's second law of motion for this free body diagram. So what is this Newton's second law of motion? Accelerating couple, that is I theta double dot, it is also known as accelerating torque, is equal to summation of external couple. So summation of external couple is due to Fs1, due to Fs2 and due to this kt theta. So we have to add all these three and all are in anti-clockwise direction, so we have to use the negative sign. So Fs1 plus Fs2 into L, that is we have to use minus 2kxl minus kt theta. Now this x is equal to L theta. So we have relation in between x and theta. So we will apply here and we can write I theta double dot is equal to minus 2kl square theta minus kt theta. So here theta is the common term and we will transfer all these terms to the left hand side. And coefficient of theta double dot is I. So we will divide the whole equation with I. So here theta double dot plus 2kl square plus kt divided by I bracket complete theta is equal to 0. So this is the simplified form. Now we have to find out the value of I. So if we observe, I is the mass moment of inertia for this rigid rod. So mass moment of inertia for the rod about the center G. What is this I? So I is equal to M for this rigid rod ml square by 12. But at the same time this rod is pivoted about this point O. So again we have to find out the distance from this center to this point O. So the center is the middle point. So what is the distance from O to the center point G? So it is L by 2. So we have to add here M multiplied by this L by 2 square. That is L by 2 bracket square. Now we will simplify this. So how we can simplify? So I will write here ml square by 12 plus m L square by 4. Now again we will simplify this. Here 4 ml square divided by 12. So here again final answer is ml square by 3. So this is known as the parallel axis theorem. Now we will put the value of I in this equation and we will simplify this. So ml square by 3. 3 will transfer in the numerator. So theta double dot plus 3 in the bracket 2kl square plus kt bracket complete divided by ml square theta is equal to 0. Now we will multiply inside. So 6kl square plus 3kt divided by ml square theta is equal to 0. Now we will compare this equation with equation of simple harmonic motion. X double dot plus omega n square x is equal to 0 and therefore we can write omega n is equal to under root of this term. That is the term in the square bracket. So how we can find out the natural frequency? So natural frequency Fn is equal to omega n by 2 pi. So simply you write here Fn is equal to 1 by 2 pi under root of this whole term.
Find the natural frequency of given system.
Let us understand given system. A cantilever beam is given with modulus of elasticity E. Then the mass moment of inertia along this cross section xx, that is Ixx, and length L. It is connected to the linear spring with stiffness K and mass M. And for this system we have to find out the natural frequency. We will consider here due to its mass M, that is it is having certain mass, it is getting displaced in the downward direction through a distance x. So here we will show the linear displacement x for this mass M. As the mass M is attached to this rigid rod, or we can say cantilever beam, through this spring with stiffness K, there is the deflection delta. So we will show here this deflection delta as one end is fixed and the other end is free. So we have to show this fixed end as it is and we will connect here. So this is the initial position, that is point A, and here is the final position, point A dash, and this deflection delta we have to show here. Now for this cantilever beam, how we can define this delta? So delta is equal to WL cube divided by 3EIXX. So this XX is the any cross section along this rigid rod or cantilever beam. So along this section XX, this is the mass moment of inertia I, and that is mentioned in the diagram. So we have to consider. Now this W is due to this mass M. So W is equal to mg. So we know this relation, W is equal to mg, and it is due to the mass M connected at the end, because the mass of this cantilever beam is given as a negligible. Then we will find out the stiffness for this cantilever beam. So for this beam we will consider the stiffness K to the base A. So Ka is equal to W by delta. So when we simplify this, then for delta, this W and this W is getting cancelled. So we can write here 3EIXX divided by L cube. Now we will consider this cantilever beam with stiffness Ka will act as a spring. Then how we can redraw this diagram? So here this is the rod is connected to this spring with stiffness K. So we can say that these two are in the connected in series. So we have to redraw here. This is the one end is fixed end, the other end is connected to the spring with stiffness K, and this cantilever beam will act as a spring with stiffness Ka. So here is Ka, here is K, and the lower end of K is connected to mass M. So for this system we have to find out the natural frequency. Now value of Ka is known. Now how to find out the equivalent spring stiffness? So both are in series. So if we combine, then we will get K equivalent. Now we have formula to find out this equivalent spring stiffness when the springs are in series. So we have 1 by K equivalent is equal to 1 by Ka plus 1 by K. Now what is this value of Ka? So here is the value of Ka. So when we take the reciprocal for this Ka, we will get 1 by Ka. So we can write here L cube divide, that is we have to write denominator in place of numerator and numerator in place of denominator. That is L cube divided by 3EIXX plus 1 by K. Now again we will simplify this. So we will cross multiply. Then we will get KL cube plus this 1 into 3EIXX divided by, we will combine this denominator, that is 3EIXXK. So this is the value for 1 by K equivalent. Now we require K equivalent. So again we have to take the reciprocal on both the sides. So K equivalent is equal to 3EIXXK divided by KL cube plus 3EIXX. So we have the formula to find out omega n. So omega n is equal to under root of K by M. So this is the formula for the spring and mass system. So for spring and mass system, how to find out omega n? That is under root of K by M. That is K is this spring stiffness K equivalent and M is this mass M. So instead of K, we have to put the value of K equivalent. So K equivalent value is here. So we have to put, and in the denominator we have to place the mass M as it is. So in denominator for this term we have to keep the bracket, and then we will write the equation. Now this is the value of omega n. Now we have to find out the natural frequency Fn. So Fn is equal to omega n by 2 pi. So simply we have to write here Fn is equal to 1 by 2 pi and under root of this term.